Use the source.
Okay, we have chapters 8 and 9 here. I decided to combine chapters 8 and 9 and really just focus on the parts that I think are really important. The book kind of throws in a lot of extra stuff. I think they make it harder than it needs to be and makes you learn more things than you really need to be learning. So we're going to focus on just what I see as necessary. And what we focus on here is what will also be in the homework. So I am not going to throw anything extra in the homework. The homework will focus on what I present here. So let's just do a little review real quick. If you add or subtract the same amount multiple times, you can shorthand that. So if I have 3 plus 3 plus 3 plus 3 8 times, well, that's just 8 times 3. In a similar fashion, if I have 3 times 3 times 3 times 3 8 times, that's 3 to the 8th power. All right, and it works with subtraction. You can think of minus 3 minus 3 minus 3 as adding negative 3 8 times. So that's 8 times negative 3. And dividing by 3, you could think of that as multiplying by a third. They have the same meaning. So dividing by 3 8 times is 1/3 to the 8th power. So I want to focus on linear growth here, so section A. Now, before we talk about linear growth, let's just understand the difference here. Linear growth, that occurs when you add or subtract something every time. As we're exponential growth, that is when you multiply by something or divide, but we try to think of it as multiply by something every time. So we're going to focus on linear, which is the adding and subtracting. Here's an example of linear growth. Let's say you have $10 and each day you get another 2. So after one day, you have 10 plus $2, so $12. After 2 days, it's 10 plus 2, or 10 plus 2 times 2, which is 14. After 3 days, you notice it's 3 times 2. After 4 days, and then after n days. All right, so if we have n times, we're adding the $2, that's n times 2. That's that shorthand notation idea. So let's look at this formula. Well, where'd the 10 come from? That was what we call an initial amount. Or some people say starting value. And then what was the 2? That was my rate per day. And then n, well, that was just the number of days. Okay, and so that is the general kind of pattern for a linear growth formula. And so here is your linear growth formula. Now we use Q as quantity, and this Q sub 0, we read that as Q sub 0. The reason why is this is signifying T is equal to 0. In other words, if T is equal to 0, that's your starting amount, because you're at time 0. Okay, so that's why it's Q sub 0. R is your rate, T is your time. Now notice I say down here, this is very important, these two must match units. So in other words, if your rate is $5 per day, then your time T is in days. And vice versa, if your time is in years, then your rate must be something per year. Okay, they must always match. So let's say you have $100 and each day you get another 5. So Q equals, well, what's my starting amount? $100. And then my rate, $5 per day, and so 5 times T. We don't know T, that's the input. It's a good idea over here to remind us though, T is days, because my rate is in days. Alright, so let's do some problems where we use this. So you rent a boat, you go out on a lake, and the rental is $20 plus $10 per hour. So starting value, well, you have to initially have $20, and then my rate, $10 per hour. And I like a little note, T's in hours, because my rate is $10 per hour. So now down in here in B, how much do you owe? Well, 20 plus 10 times T. If I'm out there for 4.5 hours, we'll plug that in for T, and I believe we get $65. Let's try another one. DMAC hires a speaker for CI week. That's our Celebrate Innovation Week. And we pay them $1,000. We plan to sell tickets for the speaker at a rate of $5. So write a function describing our profit and loss. Now, for DMAX, so we're doing this from DMAX perspective. If this is DMAX perspective, if we pay a speaker, that means we've initially paid out $1,000. So in terms of DMAC, that's negative $1,000. So you got to be very careful. What's our rate? Well, that's $5 per ticket. And so 5 times T. In this case, T is actually not time. Turns out it's the number of tickets. Okay. So would we be in the red? In other words, would we be minus money if we sold 420 tickets? Well, let's find out. Let's plug in 420 for my T value. And if I do that, I believe we get $1,100. So that is a no. We make money. So we make $1,100. All right. So be very cautious. Always think of, is this money going in? Is this money going out? Is my rate a positive rate? Is it a negative rate? Be very careful. Let's consider someone who gets paid $12 per hour. So Q equals, is there any initial amount, any starting amount? No, there is not. So that's 0 plus 12T. And $12 per hour, so T is in hours here. Okay, so there it is. And we could just simplify that as what? Q equals 12T. So how would this change if we were given a $500 signing bonus? Well, that $500 signing bonus would be an initial amount. So 500 plus 12 times T. All right, and so that would be a function showing how much we get paid over time. Now, of course, you could say, well, but you don't get that $500 every week, so this formula wouldn't work on a week-to-week basis, blah, 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 blah. But generally speaking, it does what we want. Okay, how about this? I retire with a sum of $1.1 million. I plan on taking out $16,000 a month. So my quantity in this case is my money. Starting amount, well, when I retire, I start with 1.1 million. Now, every month I'm going to take out, so minus 16,000 per month. And so T is months here. How much is left after 12 years? Oh, 12 years, but my T is in months. So 12 years, 12 months a year, that's 144 months. So what's Q? Q is the 1.1 million minus 16,000 times 144, which is negative 1,204,000. So actually, if I took out $16,000 a month like that, there's no way I could last that long. Looks like I'd only end up with, actually I'd be way in the hole after 12 years. So I'd need to withdraw less, or maybe I need to delay retirement. I don't know. All right, so equations of a line. There's your two forms of equations of a line. This top equation is a lot like our Q1. It's pretty much the same thing. The other version is the y equals mx plus b, which is the slope-intercept form. So m is the slope, b is the y-intercept, which is where your line on a graph crosses the y-axis. And so your rate of change, or in other words your slope, that's the change in the y values over the change in the x values, or we can signify it on this this formula here. And so if I have this graph, you can see here's your 2 points. So this point would be like x1, y1. This is x2, y2. And then we put them into that formula and find the slope. So let's go ahead and try a couple examples. Town City had a population of 5,000 in 1930. In 1938, the population grew to 6,432. So what was the rate of change? Well, 6,432 minus 5,000. That's the change in my population over the change of time. Now, this 6,000 here goes with 1938. So since that was first on top, this has to be first on bottom. And so if you work that out, I believe you get 179. 179 what? Well, the top part's people per year. That's my rate. And it's a positive value. So what's going on? Well, my population's growing at about 179 people per year. So write an equation that models population. It's a linear equation. So initial amount. So we are going to stick with this as my initial. So 5,000 plus what? 179 is my rate times t. And since my rate is people per year, t is years. Also, where did the initial start from? The initial started in 1930, which therefore means t is the years since 1930. Okay? So that's very, very important to understand that. So if I wanted to figure out the population in 1950, I would have to plug in 20 for t, because that's 20 years since 1930. Okay? Another one, write an equation that describes the rain depth at any time after the storm began. Well, they actually give us the slope here, so the equation is Q equals, what's my initial amount? Well, initially, I had 0 rain. So 0 is the initial amount, plus, well, according to this, my slope is 0.5 inches per hour. And so that means t is hours, because my slope is per hour. So use the equation to find the rain depth after 4 hours. So plug that 4 in here for t, and I get 2 inches. All right. What about here? So first things first, find your rate of change. Find your slope. However you want to call that. So I'm going to start this point, 212 minus 32. I'm using that slope formula. And 212 goes with 100, so if 212 is first on top, 100 needs to be first on the bottom, minus 0. So what does that turn out to be? That turns out to be 1.8. So what's my equation? Q equals initial amount. What's my initial amount? Well, initially it starts at 32, a height of 32. So in other words, when at time 0, if you will, your amount is 32. My rate is 1.8. I don't know what the labels are here, so we'll just stick with 1.8, and then we'll say t. So that's using our format from before. Now, you do notice there are labels on here. So actually, this axis is always the input axis. This axis is the output axis. So rather than Q, our output is F. And rather than T, our input's actually C. So by the way, this is the formula to convert from Celsius to Fahrenheit. All right, let's do another one. Suppose a dog weighed 2.5 pounds at birth and 15 pounds after 1 year. So what's your slope? Well, after a year, it's 15 pounds. It started at 2.5. 15 pounds was 1 year later. 2.5 was at birth, so at 0 years old, if you will. So what's that turn out to be for a rate? Well, that's 12.5 pounds per year. So give a linear function to describe the dog's growth. Well, it started initially at 2.5. I found my rate or slope is 12.5 t. And then what's t? Pounds per year, so t is in years. Now, of course, this equation is not very accurate because this implies that the dog just keeps getting bigger and bigger and bigger and bigger, which we know that doesn't happen when a dog gets a couple years old. It's pretty much as big as it's going to get. So it's kind of linear growth, but you know, these things don't always fit perfectly with reality. Let's try another one. Population of a city in 1981 was 58,000. In 2010, it was 78,000 people. Assuming the growth is linear, give a function that describes growth. So again, let's find that slope or that rate of change. So we ended at 78,000. We started with 58,000. So it's the changes in the y values, if you will. And over the time periods, well, 78,000 corresponded with 2010. The 58,000, forgot a zero there, corresponded with 1981. So if you work that out, you get 689.66. And again, top number is people per bottom is years, so people per years. So let's see here. Give a function describing growth. I need to make a conscious decision here. It actually does not matter. So you can make an equation starting from 1981 or from 2010. I'm going to start from 1981 because that's when I was born. So the initial amount is 58,000. It's increasing at a rate of 68966 per year times t. So 58,000 was in 1981. Therefore, t is years since 1981. And so that would be my equation, but just clarifying that my t is measuring years since 1981. All right, now remember back in Chapter 4, you did simple interest. Simple interest is actually linear. It's a linear problem. The simple interest formula, if you remember, is P times 1 plus RT. Now, using some algebra, if you distribute, remember that means you take P times this part and P times that part. You get P plus PRT. All right, so P is the initial amount. Let's see here, the PR, that is actually your rate that you're adding, the amount you're adding due to interest, and then T is your time. So this is really Q naught plus RT. It's just we had to take P times R to get the amount you're adding every time. So example, if you deposit $15 in a simple interest account with an APR of 10%, well, see here, so A is equal to what, $15 plus an APR of 10%, 15 times, because the PR, right? Well, let's think of it this way. $15 times 10%, what's that? That is $1.50, right? So I'm going to get $1.50 in interest all the time. So $15 plus $1.50 in interest for every year. And so I could treat simple interest as a linear equation, linear growth. Last thing we need to talk about is slope and intercept. So the equation, this is the mx plus b form. Remember, this number before x, the number before your variable, is the slope or the rate of change. And this part is the y-intercept or the initial value. So the way to think about that is the initial value is always on the y-axis. So since it's -4 is the initial value, that gives us this starting point. And since the slope is 4, slope, if you remember, slope is your change in y over your change in x. So 4 as a fraction is 4 over 1. So change in y means you went up 4 and then you went over 1. And so that gives you another point, and then you could do that again, up 4 over 1 gives you another point, and those points would make a line. So let's try to put that into practice here. So let's graph these. -3x plus 7. Always start with the intercept, or the initial amount. The amount that's not with the variable is the initial amount, so 7. Now, what's -3? As a fraction, that's -3 over 1. Now remember, that's change in y over change in x. So -3 is down 3, 1 in the positive x direction. And if you have a line, and you know linear, this is linear, you know it's a line, you only need 2 points to make a line. So there's a graph of my line. Okay, let's try it again. Always start with the starting value. -3 is the starting value this time. 1/4 is my slope. So again, 1/4, it's change in y over change in x. So it's a positive 1. So I went up 1, 4 in the positive x direction. Here's my other point. And so you connect them. And if you do something like that, you just cheat like I do and make the point extra big. And that's it for graphing lines. So that brings us to exponential growth.